should start. We are very happy to have João Penedones from EPFL. He will tell us about non-perturbative Mellin amplitudes. Okay, over to you, João.
Thank you, Abhijit. Thank you, everyone, for this very nice invitation. Actually, I just found out that it's a great honor, the 75th anniversary of TIFR, to give a talk today. So, okay, so today I'm going to tell you about Mellin amplitudes, and in particular this paper we put out in December with my students João and Sasha. And I will probably mention a bit some work in progress.
Sorry, João, let me just request everyone to mute their microphones when they don't have any questions. But when you do, please do ask them.
Yes, I should have said that. Indeed, it's better if you interrupt me with questions because this system is a bit difficult for the speaker. You just speak to the silent computer. Okay, so as I was saying, yeah, this would be about Mellin amplitudes. So let me start right away with some brief motivation. So what's the context of Mellin amplitudes? Well, at least from my point of view, I like to think of it as one important piece in this bootstrap landscape. So in particular, we have two different bootstraps, or at least seemingly differently. One is S-matrix bootstrap. So it's about quantum field theory in flat space-time or Minkowski space-time, or quantum gravity, okay, if you have gravity. And the conformal bootstrap is basically the same, but applied to quantum field theory or quantum gravity in an anti-de Sitter space-time, or asymptotically anti-de Sitter space-time. Okay, and in some sense, the numerical conformal bootstrap is much more developed and more successful, and starts from functions of the boundary CFT. But equivalently, I will quickly review. We can, instead of working in position space, we can write correlation functions in Mellin space, and that's what defines Mellin amplitudes. And in this notation, so in this language, if you use Mellin amplitudes, the analogy with the S-matrix bootstrap becomes more transparent. And in fact, you can even take the flat space limit, so study the conformal bootstrap in the limit of large radius of ETS, and make a precise mapping between Mellin amplitudes, a precise limit that takes it to scattering amplitude. Okay, so this is the overall picture, and we would like to really learn how to map different questions and different equations from one bootstrap to the other. Okay, so that's the general context, but more practical is actually, can we do a more efficient bootstrap by working in Mellin space? Okay. So here we have two hints that this might be true. So one hint comes from the work of the Indian bootstrap, also known as the Indian bootstrap, the Mellin Polyakov bootstrap, where it was possible to derive many results in the epsilon expansion, large N expansion, push it even further than previous results using Mellin amplitudes. So that's one indication that, at least for some problems, Mellin amplitudes are more efficient. And then another indication is if you actually compute holographic correlators, so starting from supergravity, yes, also Mellin amplitudes turn out to be the most efficient way of writing both 3-level results and even 1-loop results. So lots of people worked on this over the past years. Okay. Okay, so that's the motivation. So in this talk, we will try to address the question of non-perturbative Mellin amplitudes. Because most of this work has been done in perturbation theory. So Mellin amplitudes basically so far has been used in perturbation theory. And we want to address the question, do they actually make sense non-perturbative? And then we want to ask how to impose the bootstrap conditions in a practical way so that we can actually use and get some physics of it. Okay, so that's the general motivation, and this is the outline. Not sure I'll be able to cover everything, but so the first part will be a bit more rigorous. We will really try to set up an existence proof for Mellin amplitudes, and then we will be a bit more pragmatic and less rigorous to try to get some practical equations. Okay, so the first thing that I want to do is just to review some Mellin amplitude basics so that everyone is on the same page. Okay, so what's the definition? So it's just a Mellin transform of the correlator in position space. Okay, so here the first equation is for generic, in position space. So it's just a Mellin transform. So the Mellin variables are exponents of the distances. But for the 4-point function of equal operators, which is basically what I will focus on today, we can really write a very explicit formula, and it's a Mellin transform in terms of the cross ratios. Okay? So, well, just a quick review. So here, the starting point, you would have 6 Mellin variables because you have 6 distances between points, but conformal invariance imposes these 4 constraints, and therefore you only have 2 independent variables, and those are your integration variables, which I choose to be GAM12 and GAM14. Okay? And so this was introduced by Mack in 2009. Okay, so why is this representation of correlation functions useful? Well, first thing is because it makes crossing manifest. So you can have, if you want, you can think of 3 independent Mallet-Stam invariants, GAM12, GAM13, GAM14. They sum to delta, that was one of the constraints, and the Mellin amplitude is invariant under permutations of these 3. Okay. Another thing that becomes manifest or becomes encoded in the analyticity of Mellin amplitudes is the OBE structure. So if you have some operator O that appears in the OBE of the external operators phi, then the Mellin amp will have poles at the position fixed by the twist of the exchange operator. Okay? This actually we will see in great detail, but it's good that you already know this general expectation. And moreover, with the definition as given here, where I factor out these gamma functions, this Mellin amplitude as a polynomial residue on this pole, whose degree is given by the spin of the exchange operator. Sorry, give me 1 second. Sorry, there was some undesired source of noise. Okay. Should be better now. Okay, and so in this language, Mellin amplitudes and scattering amplitudes become very analogous, and the analogy goes to these variables. So you think of the scattering amplitude as a function of the Lorentz invariance, the inner product of the momenta, Mandelstam invariance, and the Mellin amplitudes as a function of this gamma ij value. Okay? So they have poles with polynomial residues, and they have explicit crossing symmetry by permuting the variables. Okay, so this is what already Mack explained, and we've been using for already 10 years. But if you really ask concretely, like, okay, I give you a 4-point function, what is a non-perturbative 4-point function of a CFT? What is the Mellin amplitude? Okay, so the idea is that we would like to write a representation like that. for let's say this function of cross ratios u and b. And if you go to, well, you can go to Wikipedia and find an inverse Mellin transform, you learn that this is the integral you should compute. So you should take your function of cross ratios u and b and integrate from 0 to infinity times some powers. And that should be the inverse, that should be the Mellin amplitude. Okay. Let me just emphasize this notation. Sorry, I didn't emphasize. So I will call m hat the combination where I include the gamma functions, and Mellin amplitudes when I extract the gamma function. Okay, there's m and m hat, so don't get confused. It's just they just differ by these gamma functions. Sometimes it's more convenient to write one than the other. Okay, but the problem is that this never works. Okay, in a conformal field theory, this integral never exists. It does not converge. So what to do? Well, our idea was really quite simple, which said, let's break this integral in pieces. So this is what I show here.
Sorry, João, is there a way to see the non-convergence in some example, perhaps?
Yeah, the problem. Yes, so you see, when you go to u to 0, you would be dominated by the OPE in that channel, let's say in the 1-2 channel, the light cone OPE in the 1-2 channel. So you know that there is a divergence, like, so from the identity, you get a divergence of u to the minus delta. I think I even have that explained in the next slide. Well, it was here. Yeah, so you need, okay, you can see here at the bottom. So even to integrate just from, is there a question?
No.
So even to integrate from 0 to 1, you need the real parts of gamma 2 to gamma 4 to be bigger than delta. But then if you go to infinity, that you're controlled by the opposite OPE, by the OPE when both u and v go to infinity, which corresponds to, I guess, x 1, 3 going to 0. And there you're gonna need that the real parts, well, it's shown here. Let me, you see this picture, yeah, the real parts. So for the integral in region 1, you need to be here on the red dot. Sorry, let me, here means here. For, if you split like this, 1, 2, 3, split the integral in regions 1, 2, 3, like here. Okay. So these 3 regions are related by crossing. They are all equivalent, they are related by crossing. And now you ask, what is the region of gamma 1, 2, and gamma 1, 4 for which these integrals converge? And the answer is given here. So for region 1, you need to be in this real part of gamma 1, 2, gamma 4 bigger than delta. And then for region 2, you need to be here, which means gamma 1, 3 bigger than delta and gamma 1, 2 bigger than delta. So there is no, but since the 3 sum to delta, you cannot have the 3 of them bigger than delta at the same time. Did I answer the question? Did I answer your question, Abhijit?
Well, I didn't quite
not really
see it, but maybe as you go ahead, maybe things will clarify. So
no, I think I was too fast. So what I'm saying is, this integral, let's analyze u going to 0 and v going to 0. That is dominated by the light cone of E. Okay? The first operator is the identity. Okay? So that tells you that gamma 1, 2 and gamma 1, 4 have to be bigger than delta for this integral to converge. Because the function f, let me write it, the function f goes like u to the minus delta. Okay? Okay, and now basically you can just use crossing because 2 and 3, they are related by crossing. and 1, 2, 3 are already by crossing. So instead of having this condition for gamma 1, 2, and gamma 4, you will have for gamma 1, 3, gamma 1, 2, or gamma 1, 3, gamma 1, 4. Okay. But since these three things sum to delta, there is no region where the three of them, each one of them is bigger than delta.
Mm. Okay.
So what I was saying is that let's consider first this smaller integral just from 0 to 1. Then this integral exists. I just have to take gamma 1, 2 and gamma 4 sufficiently large, and this integral exists. Okay, and now, as I said, just using crossing, these three terms are the same, are equivalent. So I can, for each three pieces, I can write a Mellin representation, and that's what I wrote here. Okay. So first line is for region 1, second line is for region 2, and third line is for region 3. So this is almost a Mellin representation. The only difference is that the contours are all different, because each one of them you have to put the contour in this picture here. I mean, you're integrating parallel to the imaginary axis, so you fix the real part to be in this quadrant, or the real part to be in this triangle, or in this one. Okay.
Mm.
So the idea would be, okay, now that we have this representation, let's just deform these three contours to bring them together. And if we can bring all three integrals to the same contour, then we can sum the integrands, and that's the Mellin representation. Okay, so that's the trick. So if we can do it, then the Mellin representation is just the sum of these three k functions that I defined to be the integral from 0 to 1 in u and v. Okay, and for example, just one example that already teaches us something. Let's say we take generalized free theory. So the 4-point function is just that. Okay, the three channels of the 2-point function. We can compute k explicitly, the integral is elementary. And then you can sum the three k's, the three k's related to the three regions, and you get identically 0 for the Mellin amplitude. Okay, so this is already something we learned, is that the disconnected piece will not contribute to the Mellin amplitude in this definition.
Mm.
And in fact, what happens is that when you try to bring the contours to the same together, you have to cross some poles. The poles give you precisely the f's you had from the beginning. And once you get to the same contour, the integrand just sums to 0. Okay. Is there a question in the chat? Apparently some people are trying to ask questions, but they don't have microphone. Abhijit, check the chat, please.
Yeah, I checked it, but I don't think it's I'm not sure. If there was question, then if I see it, then I will let you know.
Okay.
Don't worry about it. Yeah.
Okay, so this was the basic idea. It's rather simple. So what's the next step? Next step then is, let's bring this together, these contours together. But how to do it? For that, we need to analytically continue the function k. Okay? So we need to discuss how to analytically continue this function k. So this is what this slide is about. So the function k was defined in this region here by this integral. So in this region, it's completely analytic. But now we have to deform it to smaller values of gamma 1, 2 and gamma 1, 4. And well, I will explain this a bit better, but it's clear that you will find poles. So the poles will be implied just by this form of the expansion. Okay? So this is the light cone expansion of the 4-point function. So if you expand that small u and fixed v, that corresponds to going to the light cone. So x1, 2 goes to 0. And you see basically powers of u controlled by the twist. So that this tau is the twist of the exchange operator in this 4-point function. But now you see each term which is a power in u, if you just plate it in this integral, you just get a simple pole in gamma 1, 2. Right? So it's an elementary integral of u to some power. So what we expect is, as predicted in the introduction, already predicted by Mac, that we should find these poles L to the analytic continue. And in fact, the first pole is the pole of the identity, which is tau equals 0. It's precisely this axis here. That was the first barrier. Okay. But then one should, so here I want to emphasize that the structure, the analytic structure of Mellin amplitudes is really controlled by the twist spectrum of the CFT. But we know a lot about the twist spectrum of the CFT, right? So we know that the twist spectrum is full of accumulation points. In particular, there's this double twist, this universal double twist operators that at large spin accumulate with twist 2 delta plus 2n, where n is an integer. So you see, if you have poles here, it means that you will have poles that accumulate. So you'll have an accumulation point of poles in the K function. Okay? So sometimes this is not very much emphasized. So when we say Mellin amplitude is meromorphic, strictly speaking, it's not meromorphic because it has all these essential singularities, which are accumulation points of poles. So that doesn't have branch cuts, but it has these very nasty singularities. But in fact, we don't even know if the twist spectrum is discrete or continuous. In fact, in 2D, we know it's continuous in 2D CFTs. So this works from 2 years ago. They showed that this is continuous. So in that case, you will actually have a cut of singularities. Okay? In higher D, well, we don't know. I would expect it to be discrete, but really we don't have a very strong argument for that. Okay, so this is the expectation. And now what I want to explain is that in fact, we can make this very precise. So we can show that in this region here, we only have these poles. And so let me quickly tell you this argument, how to do that. Well, let me first state the result clearly. So here it started analytic. Now I will argue that I can move to this region and these are the only poles. Then by crossing, this region will be exactly the same because you can permute gamma 1, 2, and gamma 4. And then this region here is the hard region. This region here, we only have partial results. We don't really have a full understanding, a full rigorous understanding of the analyticity then. Okay. So let me first explain briefly how to derive this analytic structure here. Actually, it's very simple. It's a bit like the trick of analytic continuation of the gamma function. So you basically add and subtract the leading singularities. Okay? So you take f with this expansion. Okay, so this is, well, there's many ways to write an OP expansion. So this is one possible way. What matters is that the coefficients A are non-negative. Basically the expansion in Z and Z bar. And then you just split. You say, let's take the first terms up to tau equal less than tau max, and the rest I call tau subtracted. Okay? So I subtract the leading singularity, u go to 0. But now you see it's easy because now the first term is now analytic in a bigger domain because the first singularity now is u to the delta minus tau max over 2 instead of u to the delta. So you have a bigger domain. And the second term, you just integrate term by term. You can just do it explicitly. You get some rational functions. The only thing you have to show is that the sum, which may be infinite, still converges. But we did that, so we can do that using the OP. Okay, so well, let me not go into these details in view of time. So in fact, you have to be careful to bound also the double light cone limit when both u and v go to 0. But we did it. It's it's possible to do it. So the conclusion is this one, that one can show analyticity of this form, where here you only have the OP poles. And you see the OP pole, so when you take a cut, you see this complex plane. So at fixed gamma 1,4, you would see this structure in the gamma 1,2 complex plane with infinite series of poles accumulating at the double twist, or actually at all twist accumulation point. And
I have a question. Sure. So when you verified convergence, should I be worried about the higher twist operators? I mean, is there a reason why the say the twist 4 or the higher twist operators should also converge?
You mean in this sum here?
Yeah.
Yes. So here, basically the only thing we used, so we used the fact that the full sum over all operators gives the 4-point function. So we have some control on the full sum, and this has to be smaller, right? Because it's a partial sum, at least when z and z are positive. So that gives you a bound on the growth of these coefficients. Well, this is in some ways related to other works on bounds on integrated sums of OP coefficients. Like Slava, Richkov et al. And Sasha also worked on that more recently.
Okay.
So yeah, at this, if you keep gamma 1,4, so if you work on this region where gamma 1,4 is above delta, then really you can rigorously prove that all sums are bounded and you only have this pole.
Okay, thank you.
Of course, you will have more poles. If you're asking, it's not just the double twist poles. You have all poles, triple twist, you will have accumulation point of accumulation point and so on. But no other poles besides the twist of the operators that appear in the OP.
Okay. Okay, thank you.
Okay, so motivated by this, we just call it a name. The simplicity expectation is that there is nothing else. Okay? So here it's harder. We don't have a rigorous proof, but we conjecture that there's nothing else. So let me just give you some flavor. Why do we think that is true? So, well, I'm very slow as usual. So let me see. Yeah, so I have this comment here at the end. So if there were no accumulation points, if you just had a function that had this analytic structure, but without accumulation points, okay, some arbitrary number of poles, but no accumulation points, then it would just follow. It would be a theorem that it could not have anything else here. Okay, so that's Bochner's theorem. Well, the theorem basically says that if you have a function that is analytic in a tube, so in a region, let me draw it here. At least if you don't know this, you will learn something fun about complex analysis. Suppose this is a region in the real parts. Okay, let me call this region omega, and the function is analytic here. So this is real part of, let's say, gamma 1,2, real part of gamma 1,4 belonging to omega. The function is analytic, f is analytic, or sorry, k, let's say, analytic. Then it immediately implies that k is analytic in the convex hull of omega, let's say omega 0, where you just make it. You cannot have any other singularity inside the convex hull. Okay, so k is analytic when the real parts are this, and the imaginary parts can be anything. Okay, that's crucial. So that's why it's called a tube, because it's some region of real parts, and then imaginary parts can take any possible value. Okay, so that's a theorem in complex analysis, and it's rather easy to prove. You use some Cauchy representation, starting just from omega of the function in full of omega 0. And you see, it's easy to generalize if you have finite number of poles, because if you have finite number of poles, you just study the function, which is the function multiplied by a zero that kills that pole. But it's harder if you have infinite number of poles, because then you have to worry about infinite products and all that, okay? So that's why we think that if the spectrum is discrete, there shouldn't be any other singularities. And we did a partial result. So this is the best we could prove rigorously, which is we could extend this triangle from the region where we understand. We could extend this extra triangle that you see here. And that's very important because that triangle contains the crossing symmetric point gamma 1,2 equals gamma 1,3 equals gamma 1,4 equals delta over 3. Okay. So this is the point where you want to bring all the three contours together. This is the point which is crossing symmetric between the three variables. So yeah. So this is sufficient to show that the Mellin amplitude exists with a straight contour. So by bringing the three contours together, and so that's what you get in the first line, just by bringing the three K contours together to this crossing symmetric point. And the second line is whatever you get by deforming the contour, you pick all the poles. And it turns out that the poles in Mellin amplitude translate into collinear blocks in position space. So that's the extra terms you get. Okay. So I should, yeah. So in particular, this is enough to show that the 3D Ising model has a non-perturbative Mellin amplitude. Okay? The only thing you have to subtract in that case is the disconnected piece. So if you take the connected 4-point function of the sigma operator, then this 4-point function does have a representation, a Mellin representation, non-perturbative. Okay. But
so João, to understand yeah. What this what this collinear block was.
So this came from, so you had three contours and you want to bring them together to sum the integrands, right? Well, when you deform the contours, you pick poles along the way. So these are the contribution of the poles that you picked along the way.
Yeah, but how to interpret this?
What is basically you're subtracting. How to interpret? Well, you're subtracting the leading singularity in the collinear limit in each channel. So, sorry, that's probably the best picture, is the picture I had here, right? So, if you want to deform this contour here, this contour here, and this contour here to the same crossing symmetric point, you will cross some poles. Okay, so these are the extra contributions. Now, in position space, what does this mean? It means that what has a Mellin representation is not the full 4-point function. Is the 4-point function subtracted by its leading collinear singularities, so that all light cone singularities are less singular than this delta over 3 point, so that you can have this straight contour.
And in the Ising model, this piece is absent?
In the Ising model, this is just a disconnected piece. It's only the identity that contributes. Yeah.
I see. Okay, got it. Thank you.
Yeah, because the gap, the next operator is the stress tensor with twist 1, and that's already after. I mean, this is the condition. The rigorous condition is this one. All twists less than 4 delta over 3, where delta is the external dimension, must be subtracted. So the only operator in the 3D Ising model is the identity that obeys this condition.
Okay. Thank you.
Okay. Well, maybe this I can do more quickly. So another alternative, instead of bringing everything to a straight contour at the crossing symmetric point, you can allow for deformed contours. Okay, so the contour is the same for all of them. So you still bring to the same contour, but this contour is not straight. It winds around like shown here in this picture, so that it passes always on the right side of the pole. And like that, you need less subtractions. Okay. You only need subtractions if the poles are really, the poles of different k functions fall exactly on top of each other, and then you cannot split it with this deformed contour. Okay, so it turns out that the only generic pinches in a generic CFT where the spectrum doesn't have a particular alignment are the identity operator and the exchange of the external operator itself. Okay? So you, I mean, there is a formula with a straight contour where you have to subtract all operators with dimension, with twist less than 4 delta over 3. And there's a formula with deformed contour where you only have to subtract these two operators, the identity and the exchange operator itself. But okay, this is not so crucial. Well, there's some details about these pinches. Let me skip this. Okay, any question about this?
Hello.
Yes.
Joe? Yeah. So maybe you will talk about it later. Then like you can just postpone my question. But these pinches and these collinear singularities and so on and so forth, what do they correspond to in the flat space limit? If I think of like taking some flat space limit in the dual ADS or something. If it is if there's a straightforward answer to that question. Like, what are you exactly subtracting?
Yeah.
Or they don't contribute in the limit? Or...
Well, we know that the identity is disconnected pieces, but that's very specific. You see, so these subtractions are important to write this precise relation between the Mellin amplitude and the position space correlator.
Mm-hmm.
But then it's not like you need to worry about these subtractions when you take the flat space limit. The Mellin amplitude by itself will already know everything about the flat space limit.
Okay.
I don't think these subtractions really are really important for the flat space limit. They have any.
Yeah. What I'm trying to get at is what is the? I mean, what are the things that are being subtracted? I mean, you described it. What happens at the level of complex analysis and so on, but but what are we doing? Let's say in OP expansion. Is there some?
The OP expansion, we are subtracting the exchange operators with twist less than 4 delta over 3. So we're making all light cone OPs softer, less singular, so that they can all be, so that the resulting function is sufficiently soft in all light cone OPs that it can be Mellin transformed naively with just integrating from 0 to infinity in U and V.
But is there some way to see naturally whether this is a correct thing to do from a CFT even without Mellin amplitudes? Like why we have to subtract things with 4 delta over 3 gap? Yeah. If there's no simple answer, it's okay. I'm just curious.
Yeah, the 4 delta over 3 comes from, I mean, it's, I guess I'm just giving you a technical answer. Perhaps you want something deeper, I don't know. So this is the power you will get from an operator of twist tau. And since you want to be at the crossing symmetric point, which is delta over 3, you need the singularity to be softer than delta over 3, and that's how you get the 4 delta over 3. It's just comparison with the value at the crossing symmetric point. But yeah, I don't have a better answer to give you. I don't know.
Okay, yeah, thanks.
Joe, just to make sure I got the story straight. So this formula that you've written in the beginning of this slide here, this is valid for any external operator dimension delta phi. It's not, there is no restriction on delta here. I mean, for example, can I take delta to be large in this formula?
But well, you pay a price, right?
Yeah, sure. I'll have to do a lot of subtractions, but at least in principle, I can do it.
So, okay, I think it's true, but rigorously what we proved was this scenario here. And here we cannot do that. So here it's important that the exchanged operator, the external operator is actually the minimal twist.
I see.
Because you see, because we could only go, actually the barrier that we could not cross here is the accumulation points of triple twist operator. So if you have an operator which is heavy, much heavier than the lightest operator, you have to cross, I mean, you will see accumulation points of the light operator, double and triple and fourth operator of the light operator much before you get to the heavy scale, right? So
right.
that we cannot do. So,
so do you have any understanding?
The way it was rigorously derived was only for the external being delta. Then you can probably do a bit better. You see, there is a bit of space between the crossing symmetric point and this line, but not much. So the rigorous, but honestly, I think this might be improvable because you just have to understand better your B coefficients of triple twists to kind of bound their sums.
I see.
Which we didn't really explore.
Okay, João.
Yes.
So going back to the point that Logar is, so I always thought that this identity, the disconnected piece that you subtract, it's like in the flat space limit, you are not, you're just looking at the T matrix, not the S matrix. I mean the interacting part, right? And the disconnected part is just the delta function propagation, right? But now that you are telling me that I should subtract more, and then they correspond to operate some twist and so on. So I would have thought that you're subtracting some physical particles with low mass.
Yeah, I'm not saying that these exchanges that I'm subtracting here should be thought as disconnected pieces in flat space. No, I'm not saying. I just said as an example, so for even in the Eisen case, indeed the subtraction is disconnected, which we understand. This one, I don't think this subtraction, I don't know of any physical meaning of this subtraction in the flat space limit. Let's make it.
Okay.
It's
You
also
would still say that take M and then compute the flat space from there, from this M.
Well, you can compute the flat space from this M and you will get the full T, as you said. There's not going to be any subtraction.
Yeah.
Subtraction is just in the relation to the position space.
Yeah.
In particular, the Mellin amplitude will still have poles due to these subtractions that are not the identity. So even if you subtract, it knows about them.
Yeah, exactly. Thanks, João. Yeah, that's an important comment, indeed. So it's not like the Mellin doesn't have these poles. It has them, but they are basically on the other side of the contour. That's why the subtraction is there. But the Mellin amplitude still has these poles. That's why you can introduce a deformed contour where you pass on the other side of these poles and then you don't have to subtract them. Okay, so this is a comment. Yeah, so this is a comment that partially justifies these gamma functions from a new perspective, the gamma functions that we factor out from the Mellin amplitude. And this is something standard in the mathematical literature in Mellin transforms. So if you want to understand the behavior, the asymptotic behavior of a Mellin transform, that is related with the analyticity in a sectorial domain. Okay, so a sectorial domain is when you take, let's say, U and V to be any positive real number times a phase. Okay, so the phase I call arg U and arg V. And now you ask, when is F analytic for any values of modulus of U, modulus of U, and V, and fixed argument U and V. Okay, so you, for example, if arg-U and arg-V are 0, this is just the original section, U and V bigger than 0. But now you can ask, when you rotate U and V, what is the analytic domain? And okay, this you can do some work using the OPE. So you have 3 channels where the OPE converges. And so we did this carefully and we obtained this domain. Okay, so this is, well, there's here some colors. Each color corresponds to one OPE. And the overlap of all OPEs shows that the region where the sectorial domain where the function is analytic is this one. Okay, so I can deform the phase of U and V inside this region, and the function will still be analytic. So now you might ask, well, let's try to understand this from the Mellin representation perspective. Okay, so what does this mean in Mellin representation? Well, in Mellin representation, you have F given as an integral. And now if you put phases on U and V, you get this exponential factor, which actually grows exponentially because you're integrating along the imaginary axis in gamma 1, 2 and gamma 1, 4. So these imaginary parts are going to infinity. So if arg-U and arg-V are not 0, you get an exponential growing factor. So if you want this representation to be valid and obtain this analyticity in this sectorial domain, better be that this Mellin amplitude, or this M hat, is exponentially suppressed like this supremum. So this just means that this exponential suppression is sufficiently strong to beat this exponential growth for any arg-U, arg-V inside this region. Right? It's basically the growth of this is killed when you are at the boundary. And now it turns out that if you analyze the growth at large gamma 1, 2 and gamma 1, 4 of this product of gamma functions, it's exactly this exponential suppression. Okay? So just use Stirling approximation for the gamma functions, it comes out like that, which would imply that the Mellin amplitude is polynomially bounded. Okay? So that's, if you want, another perspective on why it's natural to factor out these gamma functions. So I put here this comment naive because this is not really a proof. And again, we failed to give a rigorous proof, because to really give a proof, you need an extra condition. You need that the actual function is not just analytic in this domain, but is polynomially bounded when you vary U and V inside this region. Okay, and we could bound almost every region, but there is some double light cone limit that we could not fully bound. We think it's true, but we couldn't do it really rigorous. So this is not. I just wanted to be honest with you. This is probably correct, but needs to be improved. Okay, so I'm really quite slow today. So let me go into the probably the most interesting part for you, at least for Aninda and Rajesh, that they were using these Polyakov conditions intensely in their Mellin Polyakov bootstrap. So from our point of view, then, what are these Polyakov conditions? So these Polyakov conditions are, well, naively is extremely simple to understand. So the Mellin amplitude was defined as this M hat was the sum of 3 Ks divided by these gamma functions. Well, these gamma functions have poles and they are squared, so they have double poles. M will have double zeros. So we expect naively that the Mellin amplitude should vanish when this variable gamma 1, 2 goes to a negative integer, and it should even vanish quadratically. So even if you divide by gamma 1 2 plus 1 times n, it should still vanish. But this is quite naive because we just learned, or actually this we knew already for a long time, that these points are actually accumulation points of poles. These are precisely the points where the double twist operators accumulate. So what does it mean to say that a function vanishes at an accumulation point of poles, right? We have to clarify this statement. So this is the picture. So you have here the complex plane of gamma 1 2 at some fixed value of gamma 1 4. And we know that there are poles associated with the double twist Resi trajectories, which at large spin, so here so this is spin grows like that, right? And spin equals infinity accumulates at that point. And so what we're asking is, what is the behavior of the function at this accumulation point? So this is, I think it helps to do the analogy with the Veneziano amplitude, right? So when you ask the Regi limit of the Veneziano amplitude, we also ask the behavior when s goes to infinity of a function that has an infinite series of poles on the real s-axis. Right? So s equals infinity is also an accumulation point of poles in the s complex plane. So what we really mean is we want to approach this pole from any direction in the complex plane except the poles. And we want to know what's the behavior. And indeed, what we'll see is that it's a Regi-like behavior. Okay, so it will be a power law in gamma 1 2 with the exponent that depends on the other variable that is kept fixed gamma 1 4. Exactly like in the Regi limit of the Veneziano amplitude, where you take s to infinity and the exponent depends on t. So that's what we expect non-perturbatively about these points. Okay.
João, this analytic structure with the poles is for M, right? Not M hat.
Well, both are the same, right? They just the difference between one and the other in this neighborhood is multiplying by gamma 1 2 squared, right? One of the gamma functions as a. So it will just change the power that you approach this accumulation point by 2.
Okay. Thank you.
Okay, so then that's the question, and we then actually it's not hard to estimate how does the function behave as you approach this accumulation point. And so this is done here schematically. So let's take, for example, it's convenient to take this combination. Well, anything goes, but let's do it with this combination, it's a bit simpler. And let's just consider the contribution from all poles that accumulate at gamma 1 2 equals 0. This first Polyakov condition. So we just have poles at given by the anomalous diameter twist, the anomalous twist, which we know from large spin, it goes like that. And the residues of the Mellin amplitude, well, times gamma 1 2 because I chose to do it like that. Well, the residues we also know, they are Mach polynomials times the OP coefficients which approach generalized free field. So that's the large spin bootstrap. We know that at large spin OP coefficients approach GFF, generalized free field. So we can just do it and we get this kind of behavior, okay? This kind of power law behavior with J controlled by tau gap. So that's the twist of the first exchange operator. And so we have these poles that accumulate. We only care about large spin, so we can change the sum into an integral. And so we can just do it. And we arrive at this conclusion. So first is that this sum only converges if gamma 1 4 is in this interval here. So gamma 1 4 was the variable that was kept fixed. It has to be kept fixed in this interval, otherwise this does not converge. And if it's in this interval, you will find this kind of, well, we call it Regi behavior, I mean, this kind of power law behavior that depends on the other variable. See, the exponent as gamma 1 2, so gamma 1 2 goes to 0, and the exponent depends on gamma 1 4. And so now the non-perturbative Polyakov condition would be, well, if this exponent is less than 1, right? So the Mellin amplitude, sorry, maybe I should write. So the Mellin amplitude is just what is here, is gamma 1, 2 squared times n hat in this limit. In this limit, gamma 1, 2 goes to 0. So if this exponent is less than 1, I mean, I multiply by gamma 1, 2, so I get it, it vanishes as I approach in any direction. Okay, so that's the final Polyakov condition. It's that if I approach with gamma 1, 4 fixed, I approach the gamma 1, 2 equals 0 from any direction except the real line, I will go to 0. Okay. Any question about this?
Yeah, for large gamma 1, 4, this is very negative, right?
The problem is that you see, you have here, you have two terms. You have this term and this term, so you have to both vanish only in this interval. Yeah, that's the problem.
I see. So this is a condition contingent on what? I mean, this is some universal condition, or it's contingent on some property of the CFT, or what? What is it?
Well, okay, let's be clear about it. So this is the statement that there is no operator in the CFT with twist exactly 2 delta, right? That you have the double twist trajectory, which has 2 delta plus some anomalous dimensions, and we took into account all that contribution, and then we said, okay, there's nothing else at 2 delta. So in some sense, it's like elastic unitarity in flat space, that once you take into account the 2 particle states, there is nothing else. So in some energy range, in the S matrix, unitarity is not an inequality, it's really an equality because there's no other state to go into. It's kind of the similar spirit.
I see. Okay, thank you.
Okay, and yeah, so this is a bigger picture of what we think happens, but this is still a bit preliminary. We haven't explored all these other Polyakov conditions. So if you do the same analysis, you would conclude that you can impose this leading Polyakov condition, where at every negative integer, as long as gamma 1, 4 is inside this red region, so you can impose the gamma 1, 2 equals 0, minus 1 in this interval, in this red region. And the subleading Polyakov condition, which would be like M as a double 0, you can impose in a smaller region. Okay, you have to be inside this region, this green region, because the range of gamma 1, 4 gets decreased if you do exactly the same analysis. So in particular, let's say this plot is done for the 3D Ising model. I mean, if you change variables, it will change a bit the plot, but in particular for the 3D Ising model, you cannot impose the subleading Polyakov condition at gamma 1, 2 equals 0. There is no green region there, for example. Okay. Wow. How much time do you need?
You have some time. How much time do you want?
I don't know, 10, 15 minutes, something like that.
Yeah.
Okay.
Yeah. Okay.
Okay. Let me skip this. Okay. Any question about this? So this was important yes. Because something we discussed.
Sorry, I have a small question. So is there no region of this gamma 1 to gamma 1, 4 space where the M hat behavior itself is softer than a singularity? So that you get even sub-leading Polyakov condition and whatnot.
Good. So this I should have explained better. Good. So here, let me start here, for example. So in this equation, in principle, there are more contributions. What are these extra contributions? So the contributions I wrote explicitly were the contributions from the poles that are accumulated at the point I want to study. Of course, there are poles at finite distance away, right? There's lots. So that would be a finite piece, a regular piece for m hat. But since I multiply by gamma 1, 2, actually, in this formula will be like that. Gamma 1, 2 times regular. Or, I mean, equivalent, yeah, something like that. So because of these regular pieces, you cannot impose sub-subleading, right? Because you cannot say that m hat as a 0, because there's no reason for m hat to have a 0, because there's contributions from poles at all finite distance, right? I mean, this basically is the naive reasoning here. You only multiply by a double zero, so you're not entitled to impose anything more than that.
Okay, thank you.
Okay. Oops. So let me skip basically this part. I will just state the result. So because this we basically reviewed the literature, was not something really new that we did here. So if you study the Regge limit and you translate it to Mellin amplitudes, so in the Regge limit you have some bounds of the correlation function in position space, and you translate it to Mellin amplitudes, you get an equation like that. Okay, so the Mellin amplitude cannot grow faster than linearly. Well, you have to fix gamma 1, 2 in some domain so that you are after the poles, and then you go along the imaginary direction in gamma 1, 4, and it will not grow like that. I mean, if it grows faster than that, then it would violate the Regge bound in position space once you transform back. Okay, but for our purposes, we need something a bit stronger. So we extended this, saying that it's not just in the direction of the imaginary axis, it's in any direction apart from the real axis. Because we want to do dispersion relations, so we need to bound in all directions. So this, we think it's true in examples where we have some control, it's realized. But again, this part, we don't have a rigorous proof. It would be good to have a rigorous proof, because we were going to use it to write dispersion relations. Okay. So once we have that, now we can write dispersion relations. So we know we have an.
Sorry. Question, João.
Sure.
The equation you had in your previous transparency, which was bounding Regge type growth of Mellin amplitudes, does that have a flat space implication?
Well, you know this. It's non-trivial. I don't think there is a simple answer because of order of limits, right? It's not.
Right. So I
mean, the expectation. We have the analogous expectation, but I don't think we can use it as a proof for flat space, because you have two limits, right? One limit is the flat space limit, and this is the Regge limit. And if they don't commute, then you have to argue that they commute, and that's non-trivial. I don't know how to do that rigorously.
Thank you.
Yeah, but we expect they do. I think we expect the same bound in flat space, but there is no rigorous proof.
Can I ask a question?
Is that a question?
Yes. Can you hear? Yeah. So I was just wondering the boundedness properties conditions on the amplitude, Mellin amplitude, and also this Polyakov condition that you imposed. So are these connected to any other physical constraints on the CFT, like causality, unitarity, or are these just different conditions, the boundedness and the Polyakov conditions?
No, they follow from this condition. So Polyakov condition, as I said, is really the fact that there is no new operator precisely with respect to delta. So it's just a generic expectation of the spectrum that if you have the two particle states that accumulate, the double twist operators that accumulate, there's nothing else there. this Reggie boundness requires unitarity and OP. So, I mean, the bound comes from, you take this Lorentzian limit, and in this Lorentzian limit basically is related to the Euclidean limit by some analytic continuation, which introduces some phases in the OP. There's one OP channel that still converges, but now converges with phases. So you use unitarity to say that the coefficients are positive, and therefore the sum cannot decrease. So this Reggie boundness uses unitarity and OP convergence.
Thank you.
Okay, so let's just do this dispersion relations, because I want to give you at least something concrete that we can use to get some information about CFTs. So what do? Just a standard trick in dispersion relations. The only novelty is that we start from this formula. This formula, we divide by gamma 2 and gamma 3, which, okay, I'm going to do this at fixed gamma 4, okay, and I will keep gamma 4 in this range and fixed, such that I can use the Polyakov conditions. So therefore, I divide by this, and I don't pay the price of picking up singularities as gamma 2 equals 0, gamma 3 equals 0, because I will use Polyakov conditions. And now I just write the Cauchy representation with some contour C, like I show in this picture, and then I blow it up and I pick the contribution from all poles. So the poles are OPE poles, and there are poles in the gamma 2 and gamma 3. So gamma 4 is kept fixed, so you don't see poles in that. And that's the formula you get. And this residue of Mellin amplitude we know we can express in terms of Mach polynomials. And the final formula is the formula you see here in red. Okay. So in some sense, I think this is, this formula replaces the formula that, the starting formula of the Mellin Polyakov bootstrap, where we write the Mellin as a sum of 3 Witten diagrams, where each Witten diagram is the sum of poles. Essentially, I think the formula which we can justify non-perturbatively is like is a dispersion relation, so you only have a sum over 2 poles, because one variable is kept fixed, so you see the poles on the other 2 channels. And we have to be careful because it only converges in a specific region. Okay. So this formula makes crossing manifest between gamma 2 and gamma 3, because we kept gamma 4 fixed, so these 2 variables are still treated equally. But the crossing, for example, between gamma 2 and gamma 4 is clearly not manifest. And if we impose it now in this equation, we get some rules. We get constraints on the OPE data. Okay. So I will show you some rule that we studied in great detail. So we choose to write, so this is gamma 2 and this is gamma 4, and we put both at delta over 3, and then we expand in y, so that means the only has, because of crossing, only has positive expansion, so in particular, even powers of y. In particular, the derivative must vanish, and that gives explicit, so I just wrote it to see that it's extremely explicit, gives us some rule where alpha is a functional that depends on the twist and on the spin in a very explicit way through these Mach polynomials. So any CFT, well, actually here we use this condition that delta is less than 3/4 of tau gap being the first operator exchange. Any CFT with this property should obey this sum rule. Okay, so why is this sum rule interesting? Well, first thing is that it's a extremal functional for generalized free theory. So if you plot this function alpha as a function of tau, you see that it has double zeros at all double twist operators, except the leading Reggie trajectory. So it has a single zero exactly at 2 delta, and then it has double zeros at 2 delta plus 2 plus 4 plus 6. So this actually, we did extensive numerical checks, but we could not fully prove. We think it's true, but again, we don't have an analytic proof of this statement. But you see, if this is true, then if you ask what's the maximal twist you can have in a CFT, you get that the answer is 2 delta, and the optimal CFT is the generalized free theory. Because, yeah, it will satisfy this equation just by putting operators at the zeros. And if it puts anything outside the zero, it will contribute positively. And so it will violate this sum rule. Okay, so this is the kind of stuff that we are exploring now. This sum rule, this is just one example. There's lots of sum rules that we can derive from this dispersion relation. And we're trying to use them for this epsilon expansion to see if we can recover it from here. Another thing you can do with these sum rules, okay, sorry, we can test it since we did several assumptions that were not justified. We tested it using the 3D Ising data from Davidson and Sutton, and we got pretty good agreement. You see, it's funny because in this everything contributes positively except the leading rate trajectory. So we can compute the contribution from the leading rate trajectory in the 3D Ising quite accurately because we know very well from the numerical system. And then we can compute the contribution from everything else less accurately. So there is some ... here that we don't know. And we see that it matches up to 3%. So this ... must account for 3%, this mismatch. And another thing we did was large n. So this is also very interesting because at large n, you have single trace operators that can appear with any dimension, but double trace operators that can appear only close to these double twist operators. Therefore, the sum rule splits their contribution very naturally. So you have a contribution from single trace, which you have to treat everything is of order n1/n squared. And then you have a contribution from leading Resi trajectory of double trace, which is also of order 1/n squared, but everything else is higher order. Okay.
So João, what happened to the subleading trajectories? So n equals greater than 0. That's in the rest.
That's the order 1/n to the 4th, because the anomalous dimension is already 1/n squared, and the function has double 0, so it will go like anomalous dimension squared. It only has a single 0 in the leading Resi trajectory, so that's the property, interesting property of this function. So it's really like leading Resi trajectory against everything else, basically.
Okay.
And we allowed this rest UV because if you go very high in dimension, then the 1/n expansion will break down, right? Your anomalous dimensions will be multiplied by 1/n squared, but the anomalous dimension will grow as you go higher in there. So that's why here it's harder to estimate the order of 1/n squared. In some cases, we could do it. It's positive. That's the important thing. Okay. So then,
João, can I just clarify your the way that you would actually? So there are infinite number of operators. So there are infinite number of higher spin operators with unknown anomalous dimensions. So your idea would be that you would write down several dispersion relations and then sort of extract information, OP coefficients as well as the anomalous dimensions of these infinite number of these higher spin operators by looking at dispersion relations. Is that the philosophy?
We're asking for your application for epsilon expansion, for example,
or even for the or the thing that you're talking about right now.
So, okay, right. There's two perspectives you can take. Here, I'm taking the humble perspective of just having one sum rule that has to be obeyed. You can be more ambitious and say, can I write enough sum rules that allow me to actually derive the anomalous dimensions from importing? Right. So here I am importing one, so of course I cannot get.
But these are at the level of checking that whether these sum rules are respected or not.
Yeah. So checking, we checked. So for example, I was going to show you here for scalar, it's just 0. the contribution of the single trace cancels exactly the contribution of the leading this trajectory. And for minimally coupled scalar, when you exchange a graviton, you actually get something negative. So in this case, the UV must be compensating this sum rule. Okay? It also makes sense because gravity and all dimensions grow faster with energy. But to answer your question, yes. So now we are exploring many functionals so that we can also invert to obtain the Rambo dynamic.
Right.
But maybe let me just try to conclude because I'm already over the time I asked for. So the summary here is that this sum rule passed all the tests that we could think of. And when applied to effective field theories in ADS, it cannot exclude any seemingly healthy effective field theory. So initially we thought it could, but so far we haven't found any. So if you want, this is compatible with the Garden conjecture. Any effective field theory can be completed by sufficiently high range. Yeah. Okay, since I don't have time, I will just leave you here the open questions. There is questions about improving the rigor in the initial part, where we assume at some point we started making assumptions to make progress. And then there is more practical questions which are working on now, especially here. We're trying really to see if this is an equivalent way of deriving the Mellin Polyakov. Thank you very much for your attention.
Let's unmute and clap, please.
Joe, out of curiosity, you know what I'm going to ask you. So, have you been able to derive the leading order anomalous dimension of the phi square in the epsilon expansion?
Of the phi square, not.
Yeah, not higher spin, phi square. Yeah.
Right. I see what you're saying. Yeah, we get an equation. So by imposing, essentially the equation I showed you. Sorry, let me just go back here. By imposing not just this equation, but this equation, all the odd derivatives, right? If you put here 2k plus 1, this is true for all k, right? 1, actually 0, 1, 2. So you have infinite number of derivatives like that. Crossing implies that they are all 0. So if you impose all of this, you can get all the sum rule at order epsilon square fixes all the leading twists and all the dimensions. But as you, I guess that's what you're asking, there is one variable which is kept unfixed. The phi, you can use that to be the phi square. Yeah, there is always one variable that.
But that seems like there is something missing. I mean, even when Polyakov did his original work in 1974, he was able to get the scalar anomalous dimension. So there must be something that extra that he actually put in his approach that enabled him to. I mean, not only the leading order, he got the subleading order and also the rational part of the 3-loop order, which I think is extremely non-trivial.
Yeah, I think it's so in this work of Aldai and the large spin approach to the epsilon expansion.
No, there has to be some twist 4 operators, and it's very unclean. I mean, I don't think. I mean, he has to incorporate the information about twist 4 operators, and Polyakov did not need to do any of that.
I see.
Scalar is always
we're thinking about it still, yeah. This is still not solved. But thanks.
More questions?
Now, could I ask probably very maybe two general questions? You've explained to us. You explained to us in your talk about when Mellin space amplitudes exist and their analytic properties. So, does your work suggest a new definition of what a conformal field theory is, namely a bunch of Mellin space amplitudes which obey certain certain analyticity properties and obey some boundedness conditions. So is it true that can you lay down a set of rules such that if you find any such bunch of analytic functions, you found a conformal field theory? The second part of the question is, does this simplify at large N?
Oh, sorry, what was the second part of the question?
The first part sounds crazily ambitious because it sounds like you're getting quantum gravity theories,
Right.
but it doesn't sound so crazy at large N, where you might be able to, the flat space analog of that is like a reasonable bootstrap program. So does it simplify at large? Does it become more practical at large?
Right. Right. So I agree with you that the first part, which I think we could attempt, I mean, with lots of assumptions, but we could attempt to conjecture some rules. I think we probably have already translated, I think we translated everything we know in position space to Mellin by now, so we could just state that. But I think it would not be very useful because these functions are really all these accumulation points of accumulation points. I mean, there's really nested accumulation points of arbitrary, right? So it's really not a nice function non-perturbatively. Well, okay. I guess it depends on your taste, but I don't think we will be able to write it down. While, as you say, for large N, it's completely different. Yeah, for large N, you only have a single trace, so it sounds much more like a Veneziano amplitude-like function. So there, I think also we could write rules which would again be similar to the bootstrap large N of S matrix bootstrap.
But such that it's one-to-one, right? Every time you satisfy this, you've got a conformal field theory, and vice versa. It's equivalent.
So as I said, I mean, we haven't attempted. I think if we could try to postulate something like that without a proof, because as we discussed, there's several steps where we cannot really prove. What I'm not sure is what we would gain from that. What would be the gain? Because even if we do large N, the Mellin bootstrap at large N will still be harder than the flat space bootstrap at large N. I don't see, except if it can be done numerically better. Okay, perhaps if we first, I would first try to do numerics in Mellin space to see if it works. So far, there's zero that. If we can formulate in a way that numerics works, then perhaps we can go to large N and understand why numerics works better there, because also at large N, as matrix bootstrap, numerics does not work. There is no, we cannot even bound, right? There is like this elementary question, which is, what is, suppose you fix like one global mass and you try to make the next global mass arbitrarily high compared to the first one. There is no way to exclude that. I don't know any way to exclude that, and I've tried.
But just to go off on a wing, in the 60s, people made progress by just writing down conditions and guessing an answer. Maybe if your conditions are clearly enough stated, somebody will just guess a new answer, a class of answers. Maybe this is crazy.
Okay, we will try to challenge the community. It's a good idea.
João, I have a question about this functional that you talked about. So if you could go to this large N application of this. Over here you're saying for gravity F is less than equal to 0. Sorry, F is less than 0, right? That's what you find.
F being, perhaps I didn't define F very well.
F is the sum of the two terms, the first two terms.
The first two terms that we can actually compute explicitly.
Yeah. So my question was, why is it, because these anomalous dimensions, etc., are computed so that it can produce the contribution of the single trace operator in the S channel. why is this not automatically 0? Why don't they just cancel? Because they should be the same, you know, using crossing, because that's how it was computed. The second term was computed, right?
Well, I mean, I'm not sure. I mean, the full thing should be 0. We agree on that.
No, sorry. Let me just elaborate. So you have the single trace block, let's say, in the T channel, and its contribution on the S channel operator spectrum is introduction of a bunch of anomalous dimensions and small changes in OP coefficients for the double trace. Now you take this equation that there is this S channel, T channel block equal to sum over S channel stuff, okay, and then apply the functional on that. Then wouldn't that mean the first two terms should just be the same or opposite, whatever, it should cancel?
So I suspect this is related. I mean, you have to be careful with this condition. This functional is really non-perturbative, right? So if you do first large n, you actually have operators at twist to delta, right? At leading order, that's what you have. The two particle states have two delta, have a twist to delta, right? So
Well, 2 delta plus some 1 over n squared corrections. So I'm not understanding. Sorry.
Right. So if you first keep n squared large but fixed, then there is no operator there, so you can impose the Polyakov condition. You see, first, when you impose Polyakov condition, you have to work at finite n, so that you really shift the operators from 2 delta. And then once you have the equation, you can ask, okay, now what happens when I take the limit of large n? And what happens in that case is that you can have contributions that don't go to 0 from the UV, because in the high energy operators, let's say even the double twist, right? The anomalous dimensions of the double twist, let me write it here. You have anomalous dimensions that depend on little n and j. And they grow with little n with some positive power, right? Depends on, and they are multiplied by 1 over n squared. So for little n sufficiently large, you cannot say they are small. And so you can actually, in some cases, this case of gravity is a bit harder because you have to explore large n and large spin. But for example, for the case where you have this interaction, del phi to the 4th, then the only thing that you exchange is spin 0 and spin 2. And if you apply this functional, you also get something negative, which comes from the leaving, basically the gamma 0, 2, which is negative for the right sign of lambda. But we can actually estimate that the UV contributes the same order positively, just by studying when, like there is an n star for which, sorry, let me write it. So this is order 1 for some n greater than some n star. And then from here on, you use like asymptotic formulas for OPE density of states. And you can estimate the contribution of this UV tail up to order 1 numbers. And you see that actually it's positive and it has the right sign to cancel the negative part that you computed. So there is really no contradiction that you get some positive part from heavy operator.
Okay, yeah, I need to think a little bit more about what you said. So one more question, that you know, you want to use the sum rule to impose some condition on this, you know, effective field theories. So one possibility you mentioned was if this f were to be positive, then this will not work, right?
Right.
But
if it was positive, we will exclude the theory. We would say, okay, we impose something non-perturbative about CFT, and this ADS effective field theory is inconsistent, cannot be recomputed.
right.
But
these UV operators could be low twist operators, no?
Sorry?
These UV operators could be low twist operators, no?
Well, that depends a bit who you ask. Okay, if large twist is what you call UV, or if it's just large dimension. I think here for our functional, it had to be above 2 delta, right? If you have heavy but twist is less than 2 delta, then the functional will be negative. So by heavy, I mean twist bigger than 2 delta for sure.
But physically, there could be some heavy operators with low twist also, right? Which would then compensate this stuff.
Could be, okay. That would be an interesting way if you see, but so you're saying that the lightest twist operator for a given dimension, sorry, for a given spin, you take spin 1,000,000, and the lightest twist operator is not to put the 2 particles orbiting around at very high angular momentum, is to have like some big object with
some string state or something.
Yeah, usually that has less twist, right? As more, right? To put 2 particles winding in ADS costs, for a fixed spin, costs less energy than to put a long string. Or
so that could be like string theory, right?
Sorry?
I mean, that mechanism could be like string theory, I'm saying.
No, I think if it's a string state, the twist grows like log s, right? Like log of the spin. So it will still be above 2 delta. It had to be something more weird. I mean, we don't know of anything like that. I would find that very surprising. You have to invent new operators with twist less than 2 delta, twice the mass of the lightest particle. Yeah, we don't know of operators like that in string theory, in reality.
Okay. Okay, thank you. Any more questions? Well, if not, let's thank João for a wonderful talk. Let's clap.
So it turns out that